and I think when I hand it back, I'll just solve the problems on the board. Hopefully it won't take very long. But yeah, I've obviously looked a bunch of them over. I see where we were deficient, especially in where some of the homework assignments were deficient in the first half. So you know, hopefully things will get better. I will say though that I prefer to have a test I prefer to have a low average than a high average. It's all going to get shifted at the end. Okay, that's just the thing to keep in mind. That it's all going to get shifted at the end. So it's not, you know, you guys should be used to this. It's not you versus the test, right? It's you versus everybody else in the room. Let's study together. But like I said, I'm not going to talk about any specifics. Hopefully next Tuesday or Thursday we'll have them all graded and we'll go over it in class when you guys actually have your assignment in your hand. Yeah?
Are algebra mistakes
I mean, most of the grading is based off of conceptual understanding of the material. I would put algebraic mistakes or things like I don't know how to take an integral beneath that in terms of how many.
Just algebra.
Yeah, and then even beneath that, you would have things like numerical mistakes. So yeah, we see those mistakes. They're pretty easy to recognize. They're not going to cost you.
2 points.
Right, they're not going to cost you the entire problem statement. I mean, it depends on what the problem is. Some of the parts of the problem are only like 3 points to begin with, so it's hard to, you know, state specifically. It depends on the problem. But no, I mean, like any other class, we're testing for conceptual understanding. Okay, so a little bit of review to start, just because last time we had a test, the time before that we had a review for the test, so it's been a little bit of time since we had introduced this topic of non-isothermal reactors. So that's where we're going to pick back up today, and like I said, today and probably Tuesday will be new material on these non-isothermal reactors. I think Thursday is a reasonable time where you guys would be getting your graded tests, but it might happen Tuesday, just depends. So we had if we have some PFR and we have flow in and out, but now we have an additional complexity, and that is that the temperature is changing over the course of the reaction. So it's not an isothermal reactor. So we can solve the material balance to get something that looks like this. But now there's an additional term in this expression, which is temperature, right? Because the rate equation is also a function of temperature, because rate constants are a function of temperature. So as the temperature changes, as I do the reaction, the rates change. Just like as the conversion changes as I do the reaction, the rates change. So we need another equation. We have one here, and so remember that before we had equations that look like this when dealing with a packed bed reactor, right? And so what was the second equation that we then used to help solve these problems? Right, the Ergun equation, which tells us, or can tell us, how pressure changes, not with conversion, sorry. So what about up here? What's the second equation that we have in order to relate conversion to temperature? Yeah. So just like we did the mass balance or material balance to get this equation, we can do an energy balance to get another function that relates conversion and temperature. So we had the change in energy of the system with respect to time is equal to Q dot minus the shaft work plus the sum of all of the inlet stream flow rates times those molar enthalpies of the inlets minus the sum of the exit stream flow rates and the molar enthalpies at the exit. And remember that this was Q done to the system. In other words, this is heat delivered to the reactor, not heat generated by the reactor. And this is the shaft work done by the reactor, not the shaft work done to the reactor. So it's always important when you're dealing with these energy balances to set your conventions clearly. Yeah.
Can I just do plus WS and do from the reactor?
As long as you don't screw it up later.
Okay.
The math stays the same, yeah. But again, this is how it is in the book. Yeah.
So like an agitator and a CSCR, is that work done in the reactor?
Yeah. Okay, I won't put up all the other definitions because again, this is we've put this on the board before. And you guys can see that we're neglecting things like kinetic and potential energy. We're just focusing on the internal energy, which is why we have these molar flow rates times molar enthalpies. So going into a bit more, as we continued, we saw that the difference between the molar enthalpy at the exit stream compared to the molar enthalpy at the inlet stream could be defined as a standard state molar enthalpy at some reference temperature plus the integral between that reference temperature and the temperature we care about, and inside of here is the heat capacity of that material, and then dT. And so our heat capacity is constant with temperature? No, and of course that's why we have to leave it in this integral form. But to make our lives a bit easier, we can define not delta. We can define a heat capacity average, which is just the integral T reference to T CPI dt divided by the difference in temperature. So we haven't assumed that it's constant. We haven't removed the integral. We're just hiding it inside of another term so that, for example, if I were giving you a problem in a homework or on a test, I could just tell you this value and you wouldn't have to worry about integrating the heat capacity over the temperature range specified. So it's just a bit of a shortcut. And so another thing that can become useful is just like we have a delta H of reaction, which we can put on the board a second time. So the delta H of reaction at some temperature is equal to the delta H of reaction at standard conditions. Where now, instead of having a single species heat capacity, we introduce another term, delta Cp. And this is really done for convenience. Delta Cp is equal to all the stoichiometric coefficients times the heat capacities of the individual species. And the delta H of reaction at standard conditions, right, is simply the same thing. All the stoichiometric coefficients, and then what do we multiply this by? Heats of formation. And so you can see the parallels within that equation, right? So all of those enthalpy differences caused by changing the temperature are still related to heat capacities, but we can lump them into now essentially a change in heat capacity with reaction. Yeah.
For the CP hat there, shouldn't that the balance be T minus T is T naught?
It's T.
Because otherwise you're not taking the average, you're extending it.
It should be whatever I have on the denominator here. Let me just make sure. T I naught.
And the one above it, isn't that? Don't you have to subtract the terms for HI naught as well?
No, I'm not sure what you're saying.
For H minus HI naught.
For H minus HI naught.
Don't you have to subtract the H standard plus?
Oh, did I grab the wrong equation? I might have. Hold on. It's hard when you're reviewing because you have to like skip over every third formula. Yeah, what I meant to, yeah.